Thank you for letting me speak here. I'm going to be first introducing a problem, a methodology for a problem, and then giving a plea for help. So I hope you'll bear with me. So we have certain characterization of problems in quantum mechanics we want to do, and a certain framework to do them, and some initial numerical studies, and then what needs to be done in order to make this a more reasonable approach to this kind of problem. So we start out by introducing some high-dimensional problems. We have space-time meshing. We have problems in finance like option pricing, and we have problems wherein you have to track both the position and momentum of a given particle, or of a distribution of particles. But what we care about is quantum physics. In particular, Ridge and I want to be able to characterize polarization, simple bond lengths, and other very simple parameters in 1 and 2 electron systems, with eventually moving towards our big problem, which is probably going to be lithium, considering we're doing it in 3n dimensions. So here's our problem. Here's the weak form of the Schrödinger equation. Note it's basically just the Laplacian with or perturbed by a potential weighted mass matrix, to put it in the terms of finite elements. And it's an eigenvalue problem. So we're solving for E and the solution. And the potential term has nucleus electron interactions, which lower the energy, make it harder for us to knock electrons off, and electron-electron interactions, which make it easier for us to knock electrons off, to put it in an intuitive fashion. So then, to do this high-dimensional characterization of it, we also have to impose anti-symmetry conditions on our 3n dimensional space. And this is done essentially by keeping one electron on a certain side of a hyperplane of all the previous electrons we've considered. And if anyone wants, I can explain that more, but it's a little bit of a mess. So any numerical method for the Schrödinger equation, either a three-dimensional approximation like is usually done, DFT or Hartree-Fock or any of these things, need to account for the exponential decay of the function, at least in the case of an isolated molecule. So not a metal or any of these other nasty things which you always hear the computational chemists talk about. And in the full configuration space case, you need to mesh in order to avoid the Coulomb surfaces, which are three-dimensional and singular. You don't want not numbers coming out in your numerical methods, of course. And once again, spin. So a previous approach to this is what are known as sparse grid methods, where they essentially build basis functions in the hypercube such that the limited, the mixed order is kept to be exponentially dying. So the more dimensions you have an order on, your order, they combine interval rules in such a way that you get, instead of n to the d unknowns, you get 2 to the d unknowns. It's also easy to impose anti-symmetrization, but of course you're stuck in a hypercube. So we want to be able to extend finite element methods to do more interesting domains than the hypercube. We want to be able to adapt locally where we need it. And therefore, we started to create the framework for high-dimensional finite elements. So we want sparsity because we don't want to do exponential work. We want sparse meshes, we want sparse function spaces, and we want sparse quadrature. So we start with a very simple cell formulation. We take some set of simplices and we take the tensor product of them. So for instance, in 3D we have the tetrahedron, the hexahedron, and the prism. And we denote them by tuples corresponding to the dimension of the simplices for tensor producting. So we can easily define barycentric coordinates on these as well by defining barycentric coordinates in each of the subspaces and using these to denote, say, a vertex, an edge, or a face, or the interior, in which all of the constitutive barycentric coordinates would be non-zero. So essentially the dimension of whatever facet we're indexing is the number of non-zero coordinates minus, well, so the barycentric coordinates, they have to be normalized to 1. At least one of them has to be non-zero. So these are non-normalized, but you can easily normalize barycentric coordinates, of course. So we represent ourselves as a tensor of index corner names corresponding to 1 plus the shape for each dimension. This is in order to index the barycentric coordinates. So we have, of course, if we're going to need more than one cell if we're going to have a mesh. So our shared facets are going to contain some intersection of two cells. And they're going to have a shape like cells. We can treat them like cells also. And we have connectivity mappings between facets and cell coordinates, meaning we can look at the vertices that are adjacent to a cell and a facet and create a mapping based upon this. So essentially, we inject the facet coordinates into the cell coordinates. And we can also orient against the cotangent of a given face by either geometric means, wherein we compute the dot product of the simplex induced by the base point of the facet, or we can see how it works out as a permutation against a given cell. But this is all relatively trivial details. What we really want is we want cells with a low complexity. For instance, we don't want to represent 2 to the d plus 1 minus 1 facets for a simplicial mesh, or 3 to the d facets for a hypercube mesh, in order to define the connectivity of our mesh in d dimensions. So we only want to ever represent facets that contain degrees of freedom in our problem. And we also want to only compute the cell connectivity once. And this is where this ties into previous work in parallelized codes for cell complices. You may have heard of them before. They're the sieve. And this should allow for us to do fast assembly over these type of meshes. So what we eventually want to get to is, so our definition of function spaces can also be very easily put in terms of the barycentric coordinates, wherein we have either nodal locations or polynomial order in terms of our tuples of barycentric coordinates for each subspace. So, of course, they can be expressed as addresses, either as mixed polynomial order or as where on a given face they are. We also want, eventually, to be able to take a given cell, extract what coordinates exist on it, and then build some subspace based on that. That can either be done through a Bernstein polynomial method, wherein we decide the order of a given facet on the fly, or by rationalizing that method such that it actually gives us a partition of unity, and we don't really have to worry about order. Of course, you can use standard spectral tricks like making the nodal degrees of freedom piecewise linears. So essentially just the barycentric coordinates. But this is what we eventually want to get to. So we can refine like an individual facet of lower dimension than the mesh itself. And this would allow us to, say, have very refined say like a 1 electron tetrahedron that's very refined, but the interaction of it and, say, the other electron is less refined.